We're ready to look at the last definition of acids and bases, and this definition is the Lewis definition. The Lewis definition is the broadest, most all-encompassing definition of acids and bases, as we will see as we continue on. So what is the definition? Well, the definition is, well, let me go ahead and pull this all the way up. A Lewis acid is an electron pair acceptor, and a base is an electron pair donor. So what we have is an electron pair being donated from one atom to another atom within a reaction. And whenever this happens, that a new bond is formed. So we'll be looking for that new bond being formed to try to decide where did the electron come from and where is it going. I say here that this is the broadest definition, and what I mean by that is this. The Arrhenius definition is the most narrow definition. In the Arrhenius definition, we have to have water involved, and it's defined by how something behaves in water. A little bit broader definition is your Bronsted-Lowry definition. Bronsted. In that definition, we are talking about a proton swap, a donor of an H+, and an acceptor of an H+. And things that are meet the criteria of being an Arrhenius definition will always be a Bronsted acid or base, but not vice versa. The Lewis definition is the broadest of all. Okay? So we can have a Lewis acid-base reaction that's not a Bronsted definition, but every Bronsted would fit in the category of being a Lewis acid and base. If that is true, we can take something like HCl, and we know that it's an acid, right? We know it's a proton donor. That is fitting the definition of the Bronsted. What's the opposite of a proton? It's an electron. What's the opposite of donor? It's an acceptor. So if you're doing the opposite of the opposite, you are still an acid. Now that's how I hang on to my definition, though it might be a little convoluted. All right, so let us look at finding a new bond. When we see the reaction, we need to be looking, and we're trying to define what's the acid and what's the base. The first thing we ought to do is find the bond that formed, because the donation and acceptation of those electrons is forming that bond. So is it at 1, or is it at 2, or is it at 3? Well, it's at 2. Here was bond 1. It's already there. Here was bond 3. It's already there. So we're making this bond between nitrogen and boron. Now we will always show this bond formation with an arrow that comes from the electron pairs being donated to the thing that's accepting those electron pairs. So I'm showing those electrons being donated from the nitrogen and accepted by the boron. Now the boron didn't take them on entirely and have them leave the nitrogen. That didn't happen. What happened was the boron accepted those to the point of sharing. Now based upon that, can you tell me whether or not it is compound, we'll call it X, or compound Y, that is the acid? Well, X is the acid because it is an electron pair acceptor. It is accepting those electrons from the nitrogen. That makes this the acid, and of course, this is therefore the base. All right, so we have an acid-base reaction. We've identified the acid. We have identified the base. That's typically what you have to do with Lewis acid-base reactions if you see the whole reaction. So let's look at another example. This reaction, oh, we already did that. Never mind. Let's look at another example. Now this fits the definition of a proton swap, doesn't it? Proton transfer. Something donated a proton, and something accepted a proton. So So by our definition, we can see that this guy donated, so that makes it the acid. This accepted, so it makes it the base, and we used the language like that, and this was the conjugate base, and this was the conjugate acid. All of that is language from the Bronsted definition, okay? We want to look at it by the Lewis definition. So by the Lewis definition, we need to look for the new bond that's formed. Can you find it? Here it is. That bond was nowhere to be found on the other side. We formed a bond between an H and an N. Now, how did we make that bond? Well, this electron pair had to go and be donated to that hydrogen. Now, here is the complicating thing. Yes, we formed that bond, but we can't have a hydrogen with two bonds. So what happens is these extra electrons that are making this bond right here, we know it's 2 electrons, they're just going to go and hang out only on the oxygen. So those 2 electrons that were connecting the O to the H are sitting right there. I just circled them right there. So we have what we call electron pushing. You will see this a lot in organic chemistry. We are forming a bond, okay? We made the bond and we're seeing it here. How did we make the bond? Electrons on the nitrogen were donated to the hydrogen. That hydrogen can't hold on to all of those electrons. It can only have 2. So the 2 electrons that were already here to this oxygen are donated to the oxygen, giving me that lone pair. So I walked you through that. Now with that information, does that make this still a base? Yes, it's an electron pair donor. Does that make this still the acid? Yes, it is an electron pair acceptor. So it fits the definition of the Bronsted definition if we look at hydrogens, but it fits the definition of the Lewis acid and base if we look at electron pairs. Let me back up to this one more time. Would this one fit the definition of a Bronsted acid and base? Do you see a proton being donated? Do you see a proton being accepted? No, it would not fit the definition of the Bronsted-Lowry, but it does fit the definition of the Lewis. So when we said that, as we move further and further out, the Lewis is the broadest, everything fits within the Lewis. But you can have things that fit within the Lewis that do not exist in the Bronsted. And this is an example. You don't see this as a transfer of protons, only the transfer of electrons. So that's our last definition. We won't do a lot with Lewis acids and bases, no calculations. It's just a matter of identifying who's the acid and who's the base when you're given the full reaction.